3 continents, 30 hours, and a scientific explanation that, by every calculation, should have ended this 3 weeks ago. Here is what is happening. Earth's fireball rate in 2026 hit 3.9 sigma. That is a 1 in 21,000 statistical anomaly. A rock comet was identified as the cause. Its debris window closed April 7th. Case closed, right? Then, Buenos Aires watched a green fireball cross the sky for 10 impossible seconds. 29 hours later, Vancouver Island. Sonic boom into 3 states. NASA confirmed the speed, 100 times sound. A third event, captured by a telescope camera on Maunakea that was not even looking for it. Different directions, different velocities, different hemispheres. One expiration date that nothing seems to be respecting. Stay with me, because this gets considerably unsettling from here. Before we get into it, if you are new here, hit like and subscribe to The Quiet Archivist, because we are following every thread of this story. The American Meteor Society data that crossed the 3.9 sigma line. The peer-reviewed rock comet paper that should have closed the case but didn't. And the deeply uncomfortable possibility that the near-Earth debris environment we think we understand is considerably more populated than our current surveys are equipped to show us. There are threads here that are still unraveling, and you do not want to miss where they lead. Now settle in, and let's get into it. There is a specific kind of unease that comes not from discovering something unknown, but from realizing that something you thought was understood wasn't. Scientists call this the failure of a model. Thriller writers call it the moment the door you thought was locked swings open anyway. And right now, in the spring of 2026, that door is swinging open above our heads, literally. And the explanation we were handed to account for one of the most statistically significant fireball surges in recent recorded history doesn't quite cover what we're seeing anymore. Not even close. Earlier this year, the American Meteor Society published its quarterly analysis for Q1 of 2026. What they found was not subtle. The rate of major fireball events, defined as events witnessed by 50 or more people, had roughly doubled compared to historical baseline. Not increased modestly, not ticked upward in a way that statisticians might wave away with a footnote. Doubled. And when they ran the numbers on that doubling, the statistical significance came out at 3.9 sigma. If you are not a statistician, sigma is basically how science measures how weird something is on a standardized scale. 1 sigma means mildly unusual. 2 sigma makes researchers raise an eyebrow. 3 sigma is the threshold where most scientists start treating something as a real signal rather than background noise. 3.9 sigma translates in plain language to a 1 in 21,000 probability that this happened by chance. That is not a social media rumor. That is not an excitable Reddit thread. That is a peer-reviewed level statistical anomaly sitting in published data, waving its arms at anyone paying attention. And here is the thing, science had an answer. A real one. A peer-reviewed paper published in the Astrophysical Journal, authored by researcher Paul Schober, identified a parent object responsible for a significant portion of the surge. The paper describes something called a rock comet. Not a traditional comet in the sense most people picture. No glowing tail, no icy nucleus slowly boiling off in the sunlight, but an asteroid that has been pushed into such an extreme orbit, passing so dangerously close to the sun on each pass, that the gravitational forces involved are physically tearing it apart over time. Its perihelion, the closest point in its orbit to the sun, sits at approximately 0.2 astronomical units. That is about 1/5 the distance between Earth and the sun. At that proximity, tidal forces shred material from the object's surface on every orbit. The result is a continuous trail of debris spreading along the orbital path like breadcrumbs dropped by something being slowly consumed. 282 meteors were traced back to this hidden parent, and crucially, scientists were able to define the window during which Earth would intersect that debris stream, March 26th through April 7th. That is a remarkably clean prediction. That is the kind of thing that makes the scientific method look genuinely elegant. Earth moves into alignment with the stream, the fireball rate spikes, and then, on April 7th, Earth moves past the intersection geometry, and the anomaly should begin to subside. The story had a beginning, a middle, and what looked like an end. The case was, if not fully closed, at least substantially explained by identifiable orbital mechanics and a named, characterized source. And then April 27th happened, and April 29th happened. Both of them more than 20 days after the window that was supposed to account for the global surge had already been declared closed. So now we have a harder question. Not what caused the surge, because we have a partial answer to that, and it is a good partial answer. The new question is, the one that comes after you think you have solved something, and the data, quietly, persistently, disagrees with you. Why is the sky still lighting up? What is the part of this picture that hasn't been mapped yet? And how much of that unmapped territory are we actually moving through right now, at 30 kilometers per second, completely unaware? That is what this video is about. Not the solved part. The unsolved part. The part that sits outside the model, in the 22 days after the window closed, in two different hemispheres, in events that do not share an origin point, and in the increasingly uncomfortable possibility that we are moving through a region of space that is busier, stranger, and less thoroughly surveyed than our current detection infrastructure is equipped to reveal. Time is one of the most powerful diagnostic tools scientists have when assessing whether events are related or coincidental. Randomness, statistically, tends to spread events out across a timeline in a roughly uniform distribution. Causally linked events cluster. And what happened in the last week of April 2026 clustered in a way that makes random coincidence a genuinely uncomfortable explanation, particularly when that clustering sits on top of an already anomalous background rate. Here is the timeline, laid out with precision. On April 27th, at approximately 22 hours and 51 minutes local time in Argentina, a fireball erupted over Buenos Aires. Witnesses across the city described a brilliant object moving across the sky, trailing vivid color, visible for what felt like an impossibly long duration. Reports came flooding in from Argentina, Uruguay, and southern Brazil. The event was visible across a geographic footprint encompassing tens of millions of people in one of the most densely populated regions of South America. 29 hours later, on April 29th, at 0712 Coordinated Universal Time, a second major fireball entered Earth's atmosphere above Vancouver Island on the Pacific coast of Canada. This one behaved very differently from its predecessor. It was fast, violent, fragmenting high in the atmosphere, with enough energy that the sonic boom it generated rattled windows from British Columbia south into Washington state. 135 witnesses filed official reports across 3 American states and Canadian territory, and multiple video captures were collected from dash cams, home security systems, and deliberate observers who happened to be outside at the right moment. 29 hours, 10,500 kilometers of north-south separation, 2 completely different hemispheres, 2 objects with what appear to be very different physical properties, different velocities, and, critically, different radiants. That last word matters enormously and is worth pausing on. A radiant is the specific point in the sky from which a meteor appears to originate. When debris from a single parent body enters Earth's atmosphere, all the pieces follow closely similar orbits, and they all appear to streak away from the same region of the sky. That shared radiant is how scientists identify meteor showers in the first place. All the Perseids appear to come from the constellation Perseus, all the Leonids from Leo. It is orbital geometry made visible to the naked eye. These two events do not share a radiant. they appear to originate from different regions of the sky entirely. Which means that if they are not coincidental, and the probability of two major fireball events occurring this close together in time purely by chance is already statistically low, then they were not produced by the same debris stream. They came from different directions, different orbital geometries, possibly different parent bodies entirely. Think about what that means for a moment. Imagine two lightning bolts striking two different continents within a single day, but instead of coming from the same storm system, the meteorologists tell you they originated from two completely separate weather systems that happened to be active simultaneously. You might accept that as coincidence once. But when it sits on top of an already elevated background rate, when it occurs weeks after a predicted debris window has closed, and when the broader spatial analysis of the surge already shows statistically significant clustering from multiple distinct directions in the sky, coincidence starts to feel like the laziest possible explanation anyone could reach for. Both events cleared the threshold that the American Meteor Society uses to designate a major fireball. Both generated widespread public reaction across multiple countries. Both produced physical effects. The Buenos Aires event through sheer visual spectacle across a densely populated metropolitan area, and the Vancouver Island event through confirmed acoustic effects propagating hundreds of kilometers beyond the expected range. These are not borderline cases. These are headline events sitting inside a pattern that was already headline-worthy before they occurred, and which their occurrence extends and complicates in ways the current explanatory framework does not fully address. So let us pull each one apart individually, because the details matter. The details are where the questions live. Some fireballs announce themselves with pure speed. They streak across the sky in a second or two, a flash of white or blue-white light, gone before your visual cortex has fully processed what just happened. The Buenos Aires fireball on the night of April 27th was not that kind of event. It was the other kind. The kind that lingers. The kind that gives you time to look up, fully comprehend what you are seeing, reach for your phone, unlock it, open the camera, and still have several seconds of footage left to capture before the light finally fades. Witnesses described a bright green core with an orange trailing tail moving across the sky for approximately 10 seconds. 10 full seconds. That number sounds small in isolation until you compare it to the typical duration of significant fireball events, which are generally over in 2 or 3 seconds. 10 seconds is an eternity in fireball terms. It is the difference between a gunshot and a slow, deliberate handclap. It is the kind of duration that allows an entire stadium of people to collectively look up, point, and have a shared experience, rather than just a confused afterimage. Duration tells scientists a great deal about an incoming object's physical properties. A longer atmospheric transit generally indicates one of three things, and possibly all three simultaneously. Either the object entered at a very shallow angle, grazing the upper atmosphere rather than punching directly through it along a steep descent path, or it was moving at a relatively slow velocity for a meteoroid, which extends the time available for the ablation process to consume it gradually rather than explosively. Or it had sufficient mass to survive longer before the combination of aerodynamic pressure and superheated plasma finally overcame its structural integrity. Any one of these factors alone would produce an extended visible duration. All three together would produce exactly what was observed above Buenos Aires. The color is also informationally rich. The brilliant green core results from the ionization of nickel atoms in the object's composition, reacting with oxygen molecules at the extreme temperatures generated during atmospheric entry, temperatures reaching several thousand degrees Celsius in the plasma sheath surrounding the incoming rock. Green fireball light is essentially high-temperature chemistry happening faster than you can blink, converting kinetic energy into photons through a process that is simultaneously violent and beautiful. The orange trailing tail points toward the presence of sodium, which ionizes at slightly lower temperatures than nickel and tends to persist at the trailing edge of the ablation zone, giving the event a two-toned appearance that witnesses described vividly across multiple countries. The geographic spread of sightings was genuinely remarkable. Reports came from across Greater Buenos Aires, a metropolitan area of approximately 15 million people, and extended into Uruguay and into the southern regions of Brazil. You are talking about a single atmospheric event with a potential witness population in the tens of millions. In terms of raw human observation, this was among the most widely witnessed fireball events in recent memory anywhere on Earth. And yet, as of the time of this recording, the Buenos Aires event remains one of the least well-characterized major fireballs of the entire 2026 surge. There is no confirmed trajectory reconstruction. There is no official energy estimate from any government or scientific agency. There is no meteorite recovery. The question of whether this object reached the ground in any form, disintegrated entirely at altitude, or had its terminal point somewhere over the South Atlantic remains open. Reports of a sonic boom exist in social media and witness accounts, but have not been officially confirmed, which, given the object's apparent duration, mass, and the density of the population beneath its path, is itself a puzzle worth noting. This is the central paradox of the Buenos Aires fireball. It was one of the most visually spectacular events of its type, witnessed by more people than almost any other single fireball in the current anomaly period, and yet it remains scientifically among the least understood. Millions of phone cameras capturing video are not a substitute for calibrated scientific instruments, measuring velocity vectors, fragmentation altitudes, and energy deposition rates. The fact that this 10-second green and orange atmospheric intruder above one of the most densely populated cities in the Western Hemisphere can remain scientifically undercharacterized tells us something important and sobering about the actual gaps in our planetary monitoring infrastructure. 29 hours later, on the other side of the continent and the hemisphere, the next event would be different in almost every measurable way: fast, precise, loud, and thoroughly documented. The Vancouver Island fireball on April 29th at 0712. Coordinated Universal Time is, in terms of scientific data quality, essentially the mirror image of the Buenos Aires event. Where Buenos Aires left behind spectacular footage and widespread public reaction, but frustratingly thin instrumental data, the Vancouver Island event was captured, measured, and analyzed in sufficient detail that NASA confirmed multiple physical parameters. And when you lay those parameters out together, what they describe is an incoming object that raises as many new questions as the data answers. Velocity at entry, approximately 29.5 kilometers per second. To translate that into human scale terms, that is roughly 106,000 kilometers per hour, or just over 100 times the speed of sound at sea level. Entry altitude, approximately 90.6 kilometers, placing the object at the very upper boundary of what we consider the significant atmosphere. Fragmentation altitude, approximately 62 kilometers, meaning this object survived a transit of nearly 30 kilometers through progressively denser atmosphere before the combined aerodynamic and thermal stresses finally exceeded its structural strength, and it broke apart. Ground track, approximately 89 kilometers, the projected surface path beneath its atmospheric transit. Estimated diameter, approximately 0.6 meters. Estimated mass, approximately 454 kilograms. 454 kilograms of rock moving at 106,000 kilometers per hour does not fragment quietly. The sonic boom generated by this event was heard across a substantial portion of British Columbia and propagated south into Washington state. Multiple witnesses reported rattling windows, triggered car alarms, and the kind of low-frequency concussive pressure wave that you feel as a physical sensation in your chest before you consciously process it as sound. 135 official witness reports were filed. Multiple video captures were collected. This is a well-documented event by any measure of fireball science. But here is where the Vancouver Island data becomes genuinely anomalous rather than merely impressive. The audible range of the sonic boom, the distance from the fragmentation point at which ground-level observers reported hearing it, appears to have extended somewhere between 250 and 350 kilometers. Typical audible range for an event in this energy class runs between 50 and 100 kilometers. The Vancouver Island event's acoustic footprint was 3 to 5 times wider than standard atmospheric propagation models would predict for an object of this size fragmenting at this altitude. 3 hypotheses are currently under consideration for this acoustic anomaly. The first is a multi-fragment cascade breakup. The object may have broken apart, not in a single catastrophic fragmentation event at 62 kilometers, but in a sequence of smaller fragmentations spread along its trajectory from much higher altitude through the final breakup. Each fragmentation event in the sequence generates its own pressure wave, and the overlapping pulses from multiple events constructively interfere, producing a combined acoustic signal that carries farther than any individual fragmentation would achieve alone. The 89-kilometer ground track length is broadly consistent with an extended fragmentation sequence. The second hypothesis is atmospheric ducting. Under certain temperature and pressure gradient conditions in the upper atmosphere, sound waves can become trapped in a channel and guided far beyond normal propagation distances, bending back toward Earth's surface rather than dispersing spherically into space. This phenomenon has been documented for other large bow-light events and is physically well understood. The third hypothesis is simply that the object's actual breakup altitude was lower than the reconstructed value, and that proximity to the surface translated directly into a wider ground-level acoustic footprint. None of these explanations has been formally confirmed. All 3 remain viable. The velocity of 29.5 kilometers per second places this object in an orbital category that planetary scientists associate more readily with cometary material than with typical main belt asteroid debris. Objects derived from the asteroid belt tend to arrive at lower entry velocities, generally between 11 and 25 kilometers per second, because their orbits are more circular and more closely aligned with Earth's own orbital motion around the Sun. Objects arriving above 25 kilometers per second tend to come from highly elliptical orbits, the signature of cometary bodies that spend most of their time in the cold outer solar system before swinging back toward the Sun and intersecting Earth's orbital path on steep, fast trajectories. So this object has a cometary velocity signature, but it does not match the known late April cometary showers. Neither the Lyrids nor the early Eta Aquariids show radiant directions or velocity profiles consistent with the Vancouver Island event's observed parameters. It has the velocity of something cometary, but it came from the wrong direction for the comets we know about, which means, with uncomfortable straightforwardness, that it came from something we have not yet mapped. 135 witnesses, multiple video captures, NASA-verified instrumental parameters, and at the conclusion of all that data richness, the most honest scientific statement available is origin unconfirmed. Maunakea is a dormant volcano on the island of Hawaii, rising approximately 4,205 meters above sea level into some of the clearest, driest, most optically stable air available anywhere in the Northern Hemisphere. It is home to some of the most sophisticated astronomical instruments ever built by human beings, and among them is the Gemini North Telescope, operated by NSF's NOR Lab. The Gemini North facility operates, among other systems, an automated cloud cam, a wide-field sky monitoring camera whose entire purpose is to assess atmospheric conditions before and during scientific observing sessions. This camera watches the sky not to study astronomical phenomena, but to tell astronomers whether the sky is good enough to study tonight. In April of 2026, that automated cloud cam captured fireball events multiple times within the same anomaly window we have been examining. And the reason this matters is not immediately obvious until you understand what the camera's location eliminates from the equation. One of the most persistent objections raised against fireball surge data is a statistical concern called observation bias. The argument goes, we are not necessarily seeing more fireballs. We are seeing more reports of fireballs because more people carry smartphones. More people share footage on social media, and population-dense areas generate more witness reports, simply because more people are present to witness things. Under this model, the apparent surge is at least partially an artifact of improved reporting infrastructure and social amplification, rather than a genuine increase in the actual rate of incoming material. It is a legitimate methodological concern and deserves to be taken seriously. The Maunakea CloudCam data is a direct and meaningful counter to this objection. Maunakea is not a population center. There are no millions of smartphone users looking skyward. There is no social media ecosystem of local observers sharing footage and driving up report counts. There is an automated camera running a continuous sky survey for reasons entirely unrelated to meteor detection. It is not subject to reporting bias, social media amplification, or the natural tendency of human beings in densely populated areas to collectively notice and report unusual phenomena. If it records a fireball, it is because a fireball occurred in its field of view. No witnesses required. The geographic spread of confirmed events within the 2026 anomaly period now covers 3 distinct zones across the Pacific Basin. Southern South America, represented by the Buenos Aires event above one of the continent's largest cities. The Pacific Northwest of North America, represented by the Vancouver Island event over Canadian and American territory, and the Central North Pacific, represented by the Gemini North CloudCam captures from the Hawaiian Volcanic Summit. These are not adjacent regions with overlapping atmospheric corridors. They are distributed across thousands of kilometers of both north-south and east-west separation, in locations ranging from one of the world's most densely populated metropolitan areas to a remote scientific observatory, accessible by a mountain road most people will never travel. When scientists work to distinguish a genuine increase in incoming material from a localized or reporting-biased statistical artifact, geographic distribution is one of the primary diagnostic tools. A reporting bias clusters observations in populated media-active regions. A genuine increase in the incoming flux tends to manifest across the full surface of the planet, including the remote, automated, unpopulated monitoring points that have no mechanism for over-reporting. The Maunakea data sits squarely in that second category, and its presence in the same anomaly window as Buenos Aires and Vancouver Island substantially strengthens the case that what we are observing is a real, globally distributed elevation in the rate of significant atmospheric entries. This is what a planetary scale signal looks like when you are trying to see it honestly, without the distortions of population geography. Let's spend some real time with what 3.9 sigma actually means in practice, because it is easy to say the number and genuinely difficult to feel its weight. Sigma, in statistical terminology, measures standard deviation, how far a result sits from what probability theory would predict, based on normal variation around a baseline. 1 sigma covers roughly 68% of expected outcomes in a normal distribution. 2 sigma covers 95%. 3 sigma covers 99.7%. In particle physics, the gold standard for claiming a discovery is 5 sigma, meaning a less than 1 in 3 million probability of the result being a chance fluctuation. 3 sigma is generally considered the threshold for evidence worth investigating seriously. 3.9 sigma, sitting between those benchmarks, is well past the point where anyone in a peer-reviewed context can responsibly shrug and say probably noise, 1 in 21,000. That is the probability that the Q1 2026 fireball surge happened purely by random chance. Not 1 in 100, not 1 in 1,000. 1 in 21,000. Put another way, if you ran the Q1 fireball statistics for 21,000 different years, you would expect to see a result this extreme by chance, approximately once. We do not have 21,000 years of fireball data. We have decades, which means either 2026 is an extraordinary statistical outlier, the rarest of random flukes, or something real is happening in the near-Earth debris environment. The raw numbers behind that sigma are striking on their own terms. 38 major fireball events during Q1 against a baseline expectation of approximately 18, more than double. But what makes the 3.9 sigma particularly significant is what is nested inside the count alongside the raw frequency. The average number of witnesses per major fireball event also increased dramatically, from approximately 49 witnesses per event at baseline to approximately 142 witnesses per event during Q1 2026, nearly 3 times the historical average. And witness count is a meaningful proxy for event brightness and energy. Larger, more energetic, more luminous fireballs are seen by more people across a wider geographic area. An increase in average witness count this large suggests that the events occurring were not merely more numerous. They were bigger and more energetic on average. This is the aspect of the 3.9 sigma that transforms it from interesting to genuinely alarming. We are not discussing a slight uptick in small faint meteors that newly sensitive instruments are now detecting for the first time. We are discussing a doubling of major events involving large, bright, physically significant objects, the kind that shake windows, trigger car alarms, generate sonic booms heard across multiple states and provinces, and light up the night sky across entire countries and regions. These are not the statistical whispers of background noise resolving into marginal signal. These are the shouting, window-rattling arrivals of significant masses of rock and cometary material entering our atmosphere at hypervelocity. And there is one additional statistic from the Q1 analysis that deserves emphasis before we go further: the sonic boom rate. Approximately 79% of Q1 major fireball events were associated with reported or confirmed sonic booms. Ground-level sonic booms require objects to penetrate to lower atmospheric altitudes, to survive deep enough into the air column that the pressure wave they generate remains coherent enough to reach the surface as an audible concussion. Objects that fragment at high altitudes generally do not produce ground-level sonic booms of significant amplitude. A high sonic boom rate therefore suggests that the objects arriving during this period were not just numerous and energetic, but physically robust, dense, consolidated material able to survive deeper atmospheric entry before structural failure. This kind of cohesion is associated with certain classes of stony meteorites, with metallic composition, with material that has not been repeatedly fractured and disaggregated by collisions into weakly bound rubble. Whatever is arriving, a substantial fraction of it is arriving in pieces worth noticing. Picture the night sky as a complete sphere surrounding Earth. Every point on that sphere corresponds to a specific direction in space from which an incoming object could theoretically arrive. Now imagine marking a small circle on that sphere and declaring, all the meteors this week are going to come from inside that circle. That is precisely what a single debris stream predicts. One parent body following one orbital path generates material distributed along that path, and all of that material arrives at Earth from the same apparent sky direction, the same radiant. The geometry is clean, deterministic, and fully predictable. The Q1 2026 data does not show one circle. It shows two, separated by enough angular distance on the sky sphere that they cannot both be explained by any single orbital path. When the American Meteor Society mapped the radiance of Q1 major fireball events, plotting where in the sky each event appeared to originate, they found two statistically distinct clusters in different regions of the sky. The first cluster is associated with what is called the anthelion source, a broad region of the sky located roughly opposite the sun's current position, which represents a population of objects in relatively low inclination, roughly Earth-crossing orbits, that approach from the direction of the solar system's ecliptic plane. This anthelion cluster during Q1 showed statistical significance at approximately 4.1 sigma on its own. That is already a 1 in 63,000 level anomaly for a single source population. The second cluster is associated with high declination radiance, objects arriving from steeply inclined directions, from well above the plane of the solar system. This arrival geometry is typically the signature of long-period comets on highly elliptical orbits, or objects that have been gravitationally perturbed off lower inclination paths by close planetary encounters over time. This second cluster showed significance at approximately 4.3 sigma, an even stronger statistical departure from baseline than the first. Two separate clusters, two separate sigma values, two separate orbital geometries implied. The rock comet parent, identified in the Schober paper, cannot simultaneously produce two clusters in two different parts of the sky. An object following a single orbital path generates a single radiant. This is not a matter of interpretation or modeling uncertainty. It is the fundamental geometry of orbital mechanics. One parent generates one radiant, and attempting to explain two radiants with one parent requires special pleading that the physics does not support. The implication is both simple and significant. The 2026 anomaly involves, at minimum, two distinct source populations. The rock comet explains the anthelion adjacent cluster. Something else, unidentified, uncharacterized, not yet named, explains the high declination cluster. And the late April events in Buenos Aires and Vancouver Island, occurring after the rock comet window has closed, appear to originate from directions inconsistent with either known cluster, raising the possibility of a third contributing source. The solar system is currently sending Earth correspondence from multiple senders. We have identified one return address. The others are still unknown. The Center for Near-Earth Object Studies, operated by NASA's Jet Propulsion Laboratory, maintains the CNEOS BOLIDE database, a record of large fireball events detected by U.S. government sensors, principally satellites designed to detect large atmospheric explosions. This database is a primary resource for tracking significant atmospheric entries, and it provides energy estimates, geographic locations, and timing for events above a certain detection threshold. But there is a significant detection gap built into this system, and recent research has brought it into sharper focus than it previously occupied in public discussions of planetary monitoring. A study by Peña Asensio and colleagues examined the completeness of the CNEOS database and found that a substantial fraction of mid-sized events, objects in approximately the 0.1 to 1 meter diameter range, go undetected by the satellite network. The detection rate depends on satellite geometry relative to the event's location, the altitude and trajectory angle of the fireball's atmospheric entry, the time of day, cloud cover, and the specific energy signature produced during fragmentation. The database is not a complete census of what is arriving. It is a sample, and the sampling efficiency varies in ways that are imperfectly understood and unevenly distributed across Earth's surface. For the 2026 anomaly, this matters in two compounding ways. First, the 38 major fireball events recorded during Q1 may be an undercount of the true total number of significant atmospheric entries during that period. The actual count could meaningfully exceed what the official record shows. Second, the process of identifying parent bodies, tracing observed fireballs back to source populations through statistical radiant clustering, is operating on a dataset that may be missing a substantial fraction of relevant events. If certain radiant directions are systematically undersampled because of satellite geometry or other observational biases, the statistical clusters used to identify source populations will be diluted and harder to resolve, making it more difficult to identify weak but real signals from contributing source populations. Near-Earth object surveys have improved dramatically over the past 3 decades and have now cataloged more than 95% of Earth-crossing objects above 1 kilometer in diameter. But as you move down the size scale, from 1 kilometer to 100 meters, from 100 meters to 10 meters, the fraction of the known population decreases steeply. Objects below approximately 50 meters in diameter are largely uncharacterized. Not slightly undersampled, largely uncharacterized. Estimates suggest that Earth-crossing objects in the 10 to 50 meter diameter range may number in the hundreds of thousands to millions. We have found a small fraction of them. The objects producing the 2026 fireball anomaly are almost certainly in the 0.1 to several meter range, well below any size threshold where current survey infrastructure achieves meaningful completeness. NEO-Surveyor, the space-based infrared telescope developed specifically to detect faint, dark, heat-emitting near-Earth objects that are difficult to observe from the ground, represents a meaningful future expansion of detection capability into precisely this population range. Operating in the infrared allows detection of objects with very low optical reflectivity, dark rocky surfaces that bounce little sunlight back toward Earth and are therefore systematically undercounted by ground-based optical surveys. A NEO-Surveyor is designed to find these objects before they find us. But right now, we are operating with the maps we have, and those maps leave large portions of the small body population unmarked. We explore that blank space only in the moments when it visits us. And in 2026, it is visiting us with unusual frequency, unusual energy, and from directions that our current understanding of the near-Earth debris environment does not fully account for. When an anomaly becomes publicly visible, and the 2026 fireball surge has been publicly visible enough to generate significant online commentary, it attracts explanatory proposals from across the full spectrum of scientific credibility. Engaging these proposals honestly and eliminating them with data rather than condescension is how scientific literacy actually functions. So let us do that properly. The most scientifically interesting fringe hypothesis connects the late April events to debris associated with the interstellar object designated 3I Stroke Atlas, the third confirmed interstellar object detected passing through our solar system, which attracted significant public and scientific attention due to its unusual trajectory and genuinely exotic origin. The proposal is that material shed by 3I, or objects gravitationally perturbed by its passage through the inner solar system, might eventually cross Earth's orbital path and produce anomalous atmospheric entries. The velocity argument against this is direct and decisive. Interstellar objects arrive at velocities substantially above the solar escape velocity, typically above 40 kilometers per second, and often considerably higher, carrying the kinematic signature of their origin star system's motion relative to our own. Material derived from an interstellar visitor, whether shed directly or perturbed into new orbits by its gravitational influence, would carry velocity signatures reflecting that interstellar heritage. The Vancouver Island event at 29.5 kilometers per second is simply not fast enough to be 3I debris. The Buenos Aires event, with its apparent slowness suggesting an even lower velocity, is further still from interstellar velocity territory. The physics closes this door firmly. A second circulating explanation involves military testing or classified aerospace activity. The idea that some reported events represent re-entry of classified satellites, orbital weapons systems, or other human-made objects rather than natural meteoroids. This explanation struggles against fundamental orbital mechanics. Objects in low Earth orbit re-enter at approximately 7 to 8 kilometers per second, constrained by the velocity required to maintain orbit at those altitudes. An object arriving at 29.5 kilometers per second from deep space is moving at nearly 4 times orbital re-entry velocity. Achieving that speed from a human-made object would require energy inputs far beyond any current or near-future technological capability. The fragmentation characteristics at 62 kilometers altitude and the natural spectral signatures in the observed light curves are also inconsistent with artificial re-entry vehicles. The physics closes this door too. A third hypothesis involves changes in Earth's upper atmosphere, altering the detection probability for objects that were always arriving at this rate. Meaningful changes in atmospheric density at the relevant altitudes occur over geological timescales, or in response to massive volcanic events, neither of which has occurred. The timescale mismatch is prohibitive. And finally, atmospheric changes would not explain the radiant clustering, would not explain the velocity distribution, and would not explain why the witness count per event tripled. That door also closes. What remains after elimination is the genuine scientific uncertainty, the honest frontier. Multiple contributing source populations, at least one of which has not been identified, active during an overlapping period, producing events whose parameters do not fit neatly into any single existing model. That is not a satisfying conclusion for people who want clean answers. It is, however, an accurate one. Let's come back to where we started, not to close the loop, because the loop does not close yet, but to understand precisely what the shape of the unresolved problem actually is, and why it matters beyond the spectacle of bright lights in the sky. The surge is real, 3.9 sigma, 1 in 21,000, 38 major events against a baseline of 18. Average witness count tripling from 49 to 142 per event. Sonic boom rate at 79%, indicating physically robust objects penetrating to significant atmospheric depth. The Maunakea cloud cam data removes the population density and observation bias objections. The two radiant structure, Anthelion cluster at 4.1 sigma and high declination cluster at 4.3 sigma, removes the single source explanation before the late April events even enter the picture. The late April events themselves remove the conclusion that the anomaly ended with the rock comet window on April 7th. The partial explanation is also real. The rock comet parent identified by Schober is a genuine scientific discovery. 282 meteors traced to a hidden parent object on an extreme sun-grazing orbit, actively shedding debris through tidal fragmentation, its active window precisely defined by intersection geometry. This is peer-reviewed work in the Astrophysical Journal, and it covers a real, identifiable component of the 2026 surge. It is an extraordinary piece of investigative orbital science, and it deserves recognition as such. But it is partial. It covers one radiant cluster in one portion of the sky during one 13-day window. The puzzle is larger than the piece it defines. Buenos Aires on April 27th. 10 seconds of green and orange light above a city of 15 million people. Slow, massive, persistent, visually spectacular, scientifically undercharacterized, trajectory unconfirmed, terminal point unknown. Vancouver Island on April 29th. 29.5 kilometers per second, 62 kilometer fragmentation altitude, a sonic boom carrying 3 to 5 times farther than models predict. NASA confirmed parameters pointing toward an orbital origin that matches no known mapped source. Maunakea, professional observatory, automated capture, no population bias, Central North Pacific, multiple events within the same anomaly window. 3 continents. 3 instruments. 1 29-hour window for 2 of the events, all sitting within a larger anomaly, extending across a full quarter of the year, and continuing past its supposed explanation. The 20 to 22 day gap between the rock comet window closing and the late April events occurring is not a measurement error. It is not statistical noise. It is data, and it is the data telling us, as plainly as data communicates anything, that there is at least one contributing source to the 2026 anomaly that has not been identified. At least one parent body whose debris is reaching Earth's atmosphere. at least one orbital family whose active period is not constrained by the calculations currently available. At least one thread in this picture that science has not yet pulled. The most realistic, comprehensive model, the one that fits the most data with the fewest unresolved contradictions, involves overlapping source populations, the rock comet stream for its defined window, an unidentified high declination source with unknown temporal boundaries, possibly still active, the known annual showers contributing normal background on top of an elevated baseline, and potentially additional uncharacterized contributions from unmapped debris families below our current survey sensitivity threshold. When these layers are stacked, the result looks like what we are observing: elevated frequency, elevated average energy, multi-radiant spatial structure, and temporal persistence beyond any single known source's active period. If our detection infrastructure misses a significant fraction of mid-sized atmospheric entries, and the Peña Ascencio research indicates that it does, then the numbers we have discussed throughout this video are lower bounds. The actual elevated rate of incoming material is at least as high as the observed data suggests, and likely higher. The events that generated news coverage and mass witness reports are the ones we know about. The events that occurred over open ocean, over the Antarctic ice sheet, over uninhabited boreal forest, over stretches of Pacific or Atlantic, where no automated camera was watching and no human being was present to see the sky light up. Those events exist in the blind spot. They are real. They are part of the same flux, and they are invisible to us. We have been operating with a map of the near-Earth object environment that shows the large-scale features clearly and leaves the fine structure largely blank. The 2026 anomaly is happening in that blank space, in the sub-meter to several meter range, in uncharacterized debris streams, in parent bodies too small, too dark, and too poorly positioned relative to current survey infrastructure to have been identified before their material began arriving at our doorstep. The sky above Buenos Aires glowed green and orange for 10 seconds on the night of April 27th. The sky above Vancouver Island fractured at 62 kilometers altitude on the morning of April 29th and shook windows 300 kilometers away. The cloud cam on Maunakea, watching a dark Hawaiian sky for the clouds that would interrupt scientific observation, caught something bright and fast instead. 3 events, 3 continents, 3 instruments, one 29-hour window embedded within a larger pattern that extends across a full calendar quarter and resists every attempt to explain it with a single cause. The explanation we have is real. It is peer-reviewed. It is data-supported. And it covers part of what we are seeing. The part it does not cover is not a failure of science. It is science doing exactly what science is supposed to do at its frontier, following the data to its edge and reporting honestly that the edge is closer than we expected, and that beyond it, there is more we have not yet mapped. The real question is not what caused these fireballs. It is how many sources are still out there, undiscovered, uncharacterized, shedding debris along orbital paths that we have not yet traced, contributing to a near-Earth environment that is demonstrably more complex, more populated, and more active than our current models account for. And the answer, as of right now, is we do not know. The surveys are incomplete. The detection infrastructure has blind spots. The statistical clusters in the data point to multiple origins, and we have named only one of them. We are working on it, with the tools we have, building toward the detection infrastructure we need. And in the meantime, Earth continues moving along its orbit at 30 kilometers per second through a region of the solar system that is turning out to be considerably more interesting than anyone's baseline model predicted. The sky will keep sending us data, whether we are ready to receive it or not. The question is whether we are building the instruments fast enough to read it before it arrives.